Okay, maybe we'll just move on to the last presentation of this half of the session from Chet, high resolution imaging of velocity structures at shallow depths, application to the Waimata Valley Mud Volcanoes, North Island, New Zealand.
Great, thanks for the introduction. I'll just go ahead and share my screen here. Great. Yeah, so today I'll be talking about the high resolution imaging of velocity structures at shallow depths with application to the Waimata Valley Mud Volcanoes in the North Island of New Zealand. So in this presentation, I'll be talking about how ambient noise tomography in particular can be used for this sort of high resolution imaging. So to start off, I'll describe what ambient noise tomography actually is. So ambient noise tomography is the technique of imaging the subsurface using only the recordings of ambient seismic noise. And so when I mention imaging in this context, it means measuring the seismic properties of the Earth, and we can turn that into a 3D image, which analysts can further make inferences about the geology of the area imaged. So this has a wide range of applications in especially imaging the shallow subsurface and potential environmental impacts. And it can also be used for temporal monitoring of the subsurface, such as measuring permafrost melt and other situations like that. In this case, I'll be studying mud volcanoes. So I'll start off by describing what a mud volcano is. So a mud volcano is simply just the extrusion of mud at the Earth's surface. They may be explosive or non-explosive, and some of them may be driven by geomechanical forces, and others may be driven by igneous temperature gradients. So mud volcanoes can represent a serious natural hazard and can threaten human life. They also are known to release significant amounts of methane and other gases, so they have an important environmental aspect as well. Here we have the Lucy mud volcano in Indonesia on the left here. And on the right, we have one of the recent eruptions of one of the Waimata Valley mud volcanoes. And below, we have a geological cross-section of what mud volcano is hypothesized to look like. So here, the study area will be the Waimata Valley of New Zealand. So the Waimata Valley is just north of Gisborne, New Zealand on the North Island. This places the study area adjacent to the Hikurangi subduction zone, which is important to note because mud volcanoes are often known to be associated with subduction zones, although the relationship isn't exactly clear at this point. And mud volcanoes may provide an important window into subduction zone processes. The study area suffered 2 mud volcano eruptions that have been well documented. One was in 1930 and the other was in 2018. And here we have an image of all the recording instruments that we used in this study. There were over 100 in this case. So I'll talk a little bit about the methodology that I used in this study. So the first step is to calculate or extract Green's functions. So Green's functions are simply functions that provide information about the subsurface and are calculated by cross-correlating the seismic data and are equivalent to the cross-correlation functions by a constant. So in this plot on the left, I've plotted the Green's functions stacked by distance, filtered from 0.01 to 0.1 hertz. And then once the Green's functions have been calculated, the next step is to calculate dispersion curves, which is essentially just the velocity as a function of frequency or period of the seismic velocities. And so in this case, we measure both group and phase velocity. The final step in developing a tomographic model is to invert the dispersion curves for the 3D model. So I'll show the results from that on this next slide. So on the right, we have some horizontal model slices of the tomographic model. The color represents the seismic velocity, in particular the shear wave velocity. So the warmer colors represent slow velocities and the cooler colors represent higher velocities. And here the outline, the the black outline is a measure of the uncertainty. So anything within the black outline is, we're confident in the results. I should point out that all the data for this experiment was collected before the 2018 eruption. So we can see several prominent low velocity zones located near the surface expressions. So I'll point out that the surface expressions are kind of near where these two black dots are. The one on the right is the 2018 eruption. The one on the left is where the 1930 eruption was located. So we interpret the low velocity zones within the area of the surface expression of the eruptions to be part of the mud volcano chamber and the source mud of the mud volcano. And we find that the other low velocity zones are likely part of a bentonitic geological structure known as the Dannevirke-Arnold Formation. And here I'll plot a few vertical cross sections of the model. We can see that the low velocity zone extends to about 4 kilometers in depth, which is consistent with previous estimates of the depth of the reservoir of the mud volcano. So we interpret this low velocity zone to be the reservoir of the mud volcano. And we also note a high velocity zone kind of around 5 kilometers depth. And we hypothesize that this might be the East Coast Alephan, which in this case would be the basement rocks of the area. Yeah, and we can see the two different mud volcanoes in this cross section, C to C prime, we can see less than 0.3 kilometers per second. So some of the conclusions we can make from the study is a well-defined low velocity zone was observed in an area which subsequently had a mud volcano eruption. So this suggests that future areas of mud volcanism could be identified using this technique. We were able to image the shallow subsurface structure of the mud volcano and made the following observations. The eruptions corresponded to a low velocity zone in the 3D model, and both eruptions appear to share the same reservoir at depth, and the mud volcano reservoir extends at least 4 kilometers in depth. We can also say that the low velocity zone was observed in the area of the mud volcano that erupted in 1930. So this suggests that the previous eruption sites may have the potential to erupt again, depending on the subsurface pressure conditions. So I have a few acknowledgements for this work. I'd like to thank Dr. Adebayo Oluwasian Ojo. He was very instrumental in teaching me about the methods of ambient noise tomography, and I would like to thank Dr. Hongjin Fang for providing assistance with the code, Dr. Rebecca Bell for supplying the seismic data, and Dr. Hongyu Yu for assisting with the data preparation. I'd like to also thank the members of the Pacific Geoscience Center Seismology Group for their assistance with this project. All right, any questions?
Great.
Thanks for listening, everyone.
Thanks, Chet. Any questions for Chet? Matt?
Yeah, thanks, Chet. I thought it was very interesting. I'm studying mud volcanoes as well, using different seismic methods in the Beaufort Sea, actually. So, but at a totally different scale. I was just curious about, maybe I missed something in your talk. How long were your time series?
So I think it was about 9 months of data that had been recorded in total. Yeah, sorry, I didn't include that the first time around.
Yeah, and how many stations allow you to provide that kind of resolution?
I believe it was around 100. I can't remember the exact number off the top of my head, but it was about 100. A mix of both short period and long period instruments.
Okay, thanks. Excellent presentation. Thanks a lot.
Thank you.
Paul, you want to go ahead?
Yeah, that was really interesting and very close to Gisborne, which is one of my favorite wines, the Gisborne Chardonnay. I recommend it to anybody who's likes the odd tipple. The question, and this is in the 4 arc zone really of New Zealand, and there's a lot of, having worked in there long time ago, there is a lot of very loosely consolidated sediments in that area, and I'm struggling to think of basement in that area though, and the basement is what, and I is it sort of these 4 arc metamorphics that are basically pushing on what's causing the pressure apart from just the uplift is my thing, because you got water, you got pressure, you've got, and I guess you must have earthquake disruptions, and so that's causing enough to liquefy, I guess.
Yeah, so I think figuring out exactly where the pressure is coming from is kind of hard to do with this technique. We do know that these sediments from some preliminary geomechanical modeling appear to have like a high degree of pressurization. So I think because the pressure of the overburden as well as the tectonic pressure, that creates a high degree of overpressurization, which we think is what is driving the mud volcano. And so when I mentioned the basement, I was referring to the East Coast Alklan, which is just these, maybe basement isn't the right word, but it's kind of just represents this higher velocity, these higher velocity denser rocks that were formed in place that these sediments were deposited over top is the hypothesis in this case.
So is it in a syncline? Is it the synclinal basin, and maybe gases are forming a part of this issue? Because I noticed there's quite a bit of gas exploration has gone on the East Coast there.
Yeah, I think one of the previous studies that was done in 1970, they didn't seem to think that gases were a large part of the driving factor. I don't think they really detected
interesting
an extremely large amount of gas, but
yeah, interesting.
Okay, well, great. Thanks so much, Chet.